Hi all, welcome to this lecture one of the Dynamics of Linear System crash course. Today we are going to do an introduction to the dynamics of linear systems, and my name is Aman Singh, and I am a PhD at Indian Institute of Science. Uh, the agenda for today is we will try to learn a basic definition of what a linear system is, what is its solution, and when can we consider a linear system to be stable. Then we'll go into preliminaries of controls. So we'll see what are actions, what is an output, what is full state feedback, and then uh, we'll end this lecture. So starting for the starting, we'll define what a linear system is. So linear system is of the form x dot is equal to ax, where x is the state vector and it belongs to some mm, uh, Rn. X dot is the first derivative of state, and A is a n cross n matrix. I A belongs to R n cross n. So the reason why is it called as linear system is because the state and the relation between state and its rate of change or its first derivative is a linear combination. So there is a linear relation between the state and its first derivative. So that is why it is called a linear system. So uh, and that is what is called a linear system. And if we talk about its solution, so solution of a linear system, then its solution is given by e to the power at dot x naught, where e to the power at, might be thinking, how can there be an matrix at the power of an exponential? We'll define this. X naught is the initial state, and this is the state at time t. And e to the power at is actually a matrix of n cross n, same as the order of A, and it is defined like this. It's Taylor expansion. So as you can see, the e to the power at is just a shorthand formation of this long series of matrix, and you can see if you add these terms, these are n cross n matrices. So this is the solution of this differential equation. Now let's talk about the stability of this linear system. Stability. So it turns out that eigenvalues and eigenvectors play a very critical role in determining the stability of such a system. So let's say I have a linear system x dot is equal to ax, where x belongs to Rn. Now, if uh, if A has an eigenvalue which are all negative, then it means that system is stable. But if eigenvalues of A, let me uh, reframe this. So let's say eigenvalues of A. If they are all negative, then system is stable. If any one is positive, any one of them is positive, maybe only one is positive, rest of them are negative, then system is unstable. We'll look in future lectures why that happens, but for now, this is some generic information that will help you in understanding the linear system. Now we'll move to controls of these linear system. So and the motivation of using controls is like, let's say you have a system and it has some of its eigenvalues are positive, that is system is unstable. Then these controls will help you uh, make uh, make the system stable. So you can give some control inputs which will make the system stable. And that's what the main uh, idea behind controls of the linear system is. So let's say this is our system and U is our input. This is our control input. And we get some output. We'll talk about this output in future lectures, but you can, for now, consider it to be exactly X. So basically, we give some input to the system changes its state, and we observe that state. So that what it means here. So this output or the observation, sometimes we cannot observe all the states. For now, we have assumed that we can observe all the states. So that is why y is equal to s. This is the simplified case, but it may not be possible every time. So so um, when we add controls to a linear system, we can write. So this is our dynamic system. X dot is equal to ax that we saw previously, and to add controls, we add a control input bu, where x belongs to Rn and U may belongs to Rm. Okay, which means B belongs to N cross M. So B matrix generally tells us how is those control inputs are affecting your dynamic system. So that's what B tells us. And there is something called this output Y, which we can write as Cx. So some component of x. So we can sometimes it happens that we cannot observe all the states of x. But for now, let's consider we have a full state feedback that is c is I. So c equal to I, which means we have a full state feedback. Now we have talked about output, and this is the full state feedback. Now let's assume that we want to take this observation and try to control the system. So sometimes what we do is we just multiply it with by minus k, some matrix minus k, and uh, and that's how we give the input u. So let's say we assume u is equal to minus kx. So this is possible only if we have a full state feedback and we multiply it with some matrix k, which gives us u. So putting this in our equation, what we'll get is x dot is equal to ax plus minus kx, which can be further written as a minus bkx. As you can see, this has become linear dynamical system again, and the better part is this B and K helps us to change the dynamics. So you can imagine if it in a way that, let's say, there are some dynamics x dot is equal to ax, where a has some positive eigenvalues which keeps the system unstable. Then we can use some actions uh, or controls pu, and where we are giving by minus kx, and we get to change the eigenvalues of a such that this whole system becomes stable. So we can choose b and k in such a way that the eigenvalue of a minus bk becomes negative, and hence the system becomes stable. So for the first lecture, this is I think gives you a good idea of what how to think about dynamic linear systems and how to think about its controls. In the coming lecture, we'll go into the details of these of these topics that we have studied today. Thank you.